This is P. Mabu Hussain, Assistant Professor of EEE from Institute of Aeronautical Engineering, Hyderabad. Today, in this video, we are going to discuss about the capacitance of a single-phase transmission line as well as three-phase transmission line by considering the effect of earth. Learning outcomes of this lecture are, by the end of this lecture, the students will be able to derive the expression of capacitance for a single-phase line by considering the effect of earth, and also know the how to calculate the capacitance of a three-phase line by considering the effect of earth. So, effect of earth on the capacitance, if you see, the effect of earth on the capacitance can be taken into account by the method of images, so which is also called as the mirror images, so which is introduced by the scientist Lord Kelvin. So now if you observe the figure A here, so this figure A consists of one single conductor, and this conductor has a uniform charge distribution and is at a height of h meters from the ground here. So now consider that the conductor has a positive charge plus q coulombs per meter, then an equal amount of negative charge minus q is induced on the earth here, right? So if the plus q is the charge on the conductor, so then equal amount of charge will be induced on the earth also. That means the electric field will be originate from the conductor here and will be terminated at the earth. Also, the electric field lines are perpendicular to the surface of the earth and also the conductor. So, and the electric field of two long parallel conductors, if you see, so which are having the positive charge plus q and negative charge minus q, such that its zero potential plane will be in the midway between the two conductors. If you consider the two long straight parallel conductors which are having the charge plus q and minus q like this in the figure, so then the zero potential plane, so will be in general, it will be in the midway between the two conductors, so which is shown in the figure here. Okay, and this figure shows that the earth is replaced by the image conductor here. This conductor below the line, it is called the image conductor, and this image conductor will be exactly same height from below the ground. Suppose if your main conductor is at a height h meters from the ground, so then we are going to assume one image conductor below the ground, which is a fixed conductor in the same distance h meters. Okay, and the electric field above the plane, so which is this dashed line here, right? The electric field above the plane is same as it is when the ground is present here, right? So instead of image conductor, if the ground is also present, so in the same the electric field will be the same here. Okay, so the voltage between the two points above the earth is same in both the figures, figure A and figure B here. So figure A, if you see, you are considering the earth here, and there is a one single conductor, and if the single conductor is having a positive charge plus q and the same amount of negative charge minus q will be induced on the earth here, right? So now for getting the voltage here, we are using the method of images, which is introduced by the Lord Kelvin. According to the method of images, so we are going to consider one image conductor here. So this image conductor is not actual conductor, it is a fixed conductor. So we are assuming that there is a conductor below the earth which is at a distance h meters, right? So in such a case also you will get the same potential difference between the two conductors, right? So now let us calculate the capacitance of the single phase line, so by considering the effect of earth. Okay, so now if you observe the single phase transmission line, as you know, there will be two conductors, right? So this is the conductor 1 and this is the conductor 2 here. So let us assume that the charge on the conductor will be q1 and charge on the conductor will be q2. Okay, so in a single phase transmission line, as we know, so one conductor acts as a forward conductor and the other conductor will act as a return conductor, right? So the same amount of current will flow in the both the conductors. So because of that reason, the conductor's charge also will be the same. Okay, if the conductor 1 will be having a positive charge plus q here, and the conductor 2 will be having the same amount of charge but with a negative sign minus q will be there here. And here we are also assuming that the radius of each conductor is smaller here. Okay, so for the second conductor also the radius will be the smaller, right? So these two conductors are the actual conductors. Now to consider the effect of Earth, we are going to use the method of images. According to the method of images, we have to assume that there is one fixed conductor below the Earth plane for every conductor, right? In a single phase transmission line, you will be having two conductors, right? So 1 and 2, these are the actual conductors. Now, so according to the method of images, below the Earth plane, suppose if this dotted line is your Earth plane, and these conductors are at a height h meters from the Earth plane. So in such a case, you according to the method of images, you have to assume the same conductors at a height of h meters below the Earth. Okay, so for conductor 1, you have to take the same conductor, okay, which is at a same height from the Earth plane. Okay, so conductor 1 is at a height h meters here. So in the same height below the Earth also, you have to consider another image conductor. And now the charge on the conductor above the Earth is q plus q here, and this image conductor will be having the opposite charge, so which is minus q. In the similar way, for second conductor also, you have to assume another image conductor below the Earth plane. As this second conductor is having the minus q charge, so opposite to that, the image conductor will be having, so which means that plus q will be the charge on the image conductor, right? So now, if you observe this entire figure here, so it will be there will be having 4 conductors. Okay, so 4 conductors are there here. So 2 are the actual conductors and 2 are the image conductors, right? Now by considering all these 4 conductors, we have to derive the expression for the capacitance for a single phase transmission line, right? So now for calculating the capacitance for this type of transmission line, by considering the effect of it, first we need to calculate the potential difference, right? So now potential difference between conductors 1 and 2, so you can determine by using the general equation here. So the general equation here is V12 is equal to 1 by 2 pi epsilon naught sigma m is equal to 1 to n, 1 to 4 here. So here there are 4 conductors are there. So m value will be from 1 to 4. Qm ln d2m by d1m. Okay, this formula you have to use for calculating the potential difference between the conductors 1 and 2 here. Okay. Now you expand this summation here. So then V12 can be written as 1 by 2 pi epsilon naught into if m is equal to 1, if you take, then you will get q1 ln d21 by d11 plus, if you take m is equal to 2, then this will become q2 ln d22 by d12. So then plus, if m is equal to 3, so then q3 ln d23 by d13 you will get, plus if you take m is equal to 4, then you will get this term q4 ln d24 by d14, right? So by expanding this summation, you will get this equation here. Now what is the q1, what is q2, what is q3 and what is q4? Okay, so q1, q2, q3, q4, these are the charge on the conductor 1, conductor 2, conductor 3, conductor 4 respectively. Okay, so q1 is the charge on the conductor 1, q2 is the charge on the conductor 2, q3 is the charge on the conductor 3, q4 is the charge on the conductor 4 here. Okay, now if you observe the conductor 1 here, so that the value of q1 so will be equal to plus q here, right? So plus q. So for the second conductor, the value of charge q2 is minus q. So q3 here, if you observe, the image 3 is the image conductor, so the q3 value is minus q and q4 value is plus q. Okay, so q1 is plus q, q2 is minus q, q3 is minus q, q4 is plus q. Okay, now these values we need to substitute in this equation. Okay, right, and also if the values of D11, D22 and D33 if they are any present, right, the value of D11, D22, so this value will be equal to the radius of the conductor R, and the value of D12 and D21. So if you observe, so D12, so the distance between 1 and 2 conductor and the distance between 3 and 4 conductors, both will be the same, which is equal to capital D here. Okay, so D12 will also be same as the D21. So D34 also will be same as D34. These all values will be equal to capital D. So from this figure. Okay. Now what is the distance D23? So now D23 is the distance from second conductor to third conductor. This distance. Okay. So now how you this distance is not given in the figure here. So you have to calculate by taking any one of the rectangular triangle. Now I am taking this rectangular triangle here. Now if you observe this total height from here to here, so this side is h, this side is h, so total will be 2h here, and the distance from here to here is capital D. So this value will be D square plus 2h whole square according to the Pythagoras theorem, right? So this even can be written as under square root D square plus 4h square, or 4h square plus D square also you can say. Okay, so D21, so this D23, this D23 and D14 also the same value. Okay, so D23 and D14 both will be equal to under square root 4h square plus D square. Okay, and D13 and D4 if you observe from the figure, so D13, so 13 and 24, so this total value will be equal to 2h. Okay, so now you got the value, all the distances here, and also the values of Q1, Q2, Q3, Q4 also you got. Okay, you have to now substitute the all these values in this equation. Okay, so then V12 will become, so V12 is equal to 1 by 2 pi epsilon naught as it is, and Q1 is Q here ln, so D21 by D11, D21 here is D, so this will become D by D11 will be R, so ln D by R you will get. Okay, so Q into ln D by R, and the value of Q2, so Q2 here is minus Q, so this will become minus Q ln, so D22 is smaller, and D12, so D12 here is again capital D, so the second term will be minus Q ln small r by D, so this you will get. Okay, so then if you see the third term, so here plus plus Q3 will be, the value is minus Q, so this will be minus Q ln D23, so D23 is this distance which is under square root 4h square plus D square by D13, so D13 is this distance which is 2h, so the third term will become minus Q ln under square root 4h square plus D square by 2h, this equation. Okay, so then the last term is Q4 ln D24 by D14, so here Q4 is the plus Q ln D24, D24 is the this distance which is 2h, and D14 is this distance, so this value is under square root 4h square plus D square, right? So the last term is plus Q ln 2h by under square root 4h square plus D square. Okay, so that we are writing here. So the final voltage equation is this equation, 1 by 2 pi epsilon naught into Q ln capital D by small r minus Q into ln R by D minus Q into ln under square root 4h square plus D square by 2h plus Q ln 2h by under square root 4h square plus D square. Okay, so now from this you can take Q as common in all the terms. Okay, so you can take Q common, right? So now when you take Q common, then what you will get here, Q by 2 pi epsilon naught ln D by R, and now this Q it is taken outside, then this minus ln R by D, so this can be written as plus ln capital D by small r. Okay, so then this q also taken outside, and this minus of ln underscore it 4h square plus d square by 2h. So this can be written as plus ln 2h by underscore it 4h square plus d square. Okay, similarly in the last term q is taken outside, so the remaining term is ln 2h by underscore root 4h square plus d square. Okay, so this is the equation. Okay, now so here you have the two terms, here you have the two terms, so this can be written as q by 2 pi epsilon naught into 2 ln t by r plus 2 ln 2h by 4h square plus d square. This will be under square root. Okay, so this is the, now these two and these two will get cancelled. So what you will get finally, q by pi epsilon naught into ln, so d by this is like ln a plus ln b, so this can be written as ln ab. So ln d by r plus ln 2h by underscore root 4h square plus d square, you can write it as ln d by r into 2h by underscore root 4h square plus d square. This term you will get. Okay, so now here I am taking this total term to downside. Okay, so 2h, so keep capital D in the denominator. So now you bring this to numerator here. So then what you will get from this, q by pi epsilon naught into ln d by r by 4h square plus d square by 2h you will get. Okay, so this is the value. Now this 2h also, if it is going into inside the square root, then that will become 4h square. So this will become under square root 4h square plus d square by 4h square. Now this can be written as q by pi epsilon naught ln d by r into under square root 1 plus d by 2h whole square you will get. Okay, so this is the term what you are getting finally. Okay, d by 2h whole square or d square by 4h square also you can say. Okay, d square by 4h square 1 plus. So the potential difference between the conductors 1 and 2, which is V12 is equal to q by pi epsilon naught ln d by small r into 1 plus d square by 4h square whole to the power of 1 by 2. So this value is in volts. Once you get the voltage or potential difference, then you can calculate the capacitance C, which is equal to q by V. Right. So now you want the capacitance between 1 and 2 conductors, which is the line capacitance. C12 is equal to q by V12. Okay. So now the value of V12 is this value. Now this value if you substitute here, so this q will get cancelled. So then capacitance C12, so this C12 will be equal to pi epsilon naught by ln d by r into 1 plus d square by 4h square whole to the power of 1 by 2 you will get. And the unit for this capacitance is farads, and the value is for 1 meter length of the transmission line. So farads per meter will be the unit. Okay, so now if you want to convert this farad per meter into microfarad per kilometer, so then you have to substitute the value of epsilon naught. So epsilon naught value is 8.854 into 10 to the power of minus 12 farads per meter. So this value you have to substitute here, and this ln term you have to convert into logarithmic term, right? So then after converting, the final value of capacitance between the conductors 1 and 2, C12 will be equal to 0.0121 by log d by 1 r into 1 plus d square by 4h square whole to the power of 1 by 2, and this value is in microfarad per kilometer. Okay, so now here you have the two equations. So one is in farads per meter, another one is in microfarad per kilometer. So for calculating the capacitance of the transmission line, which is a single phase transmission line, you can use any of these two equations. Okay, so if you consider the effect of earth here. Okay, now it is observed that the presence of earth modifies the radius r to r into 1 plus d square by 4h square whole to the power of 1 by 2. Right. So if the effect of earth is not considered, then the value of C12, so what we have calculated previously, is 0.0121 by log d by r. Okay, so this is the value of capacitance between the conductors 1 and 2 if effect of earth is neglected. Okay, and if you consider the effect of it, this is the capacitance equation. Now if you observe these two equations, so then this small r is replaced by r into 1 plus d square by 4h square whole to the power of 1 by 2. So this is the difference. Okay, now if you calculate the both values here without considering the effect of earth and with considering the effect of earth, so then the value of capacitance will be more in case if you consider the effect of earth. Right. In similar way, you can also calculate the capacitance of a three-phase line by considering the effect of earth. Right. Here I am giving the brief description about the how to calculate the capacitance of a three-phase line by considering the effect of earth. Right. So if you take a three-phase transmission line here, there will be three conductors. Right. Those conductors are represented here: 1A, 2A, 2B, 3C, like that. Okay, so these are the three conductors. They are represented with 1A, 2B, 3C, like that. Okay, so now here you have the ground or earth also, you can say. Now if you want the capacitance for this three-phase line by considering the effect of ground also, in such a case you have to use the method of images. Okay, so in the method of images, for every conductor you have to assume one image conductor which is below the earth. Right, and exactly in the same height. Okay, suppose if you take the conductor 1A here, so this 1A is at a distance, right? So some distance h will be there, right? So below the earth also at the same distance you have to take another conductor, right? So which is called the image conductor. Okay, like that for this conductor also you have one image conductor, and the third conductor also will be having one image conductor. Now here you have a total of 6 conductors. Okay, now by considering all the 6 conductors, you have to calculate the capacitance. Okay, right. So now before calculating the capacitance, as usual, you have to calculate the potential difference between any two conductors. Right, here we are calculating the capacitance between the conductors A and B, which is VAB here. Okay, so now before calculating this, you have to calculate the distance between all the conductors. Right, so here instead of calculating, they were assuming the distances. Right, the distance from 1A to 1A dash, this is H1, and the distance from 2B to 2B dash, this will be H2, and the distance from 3C to 3C dash will be H3, and distance from 1A to 1B is D12, and from 2A to 2B is D23, and 1A to 3A is D31. Okay, and this distance also will be the same here. Okay, so this will become the distance, this one, this distance and this distance will be the same. This distance and this distance will be the same here, and the distance from 2B to 1B we are calling it as H12, and from 3C to 1A we are calling it as H31. From 1A to 2B is H12, 1A to 3C dash is H31, and 2B to 3C dash will be H23, and 3C to 2B dash will be H23. So like that, all the distances we are assuming here with some letters. Okay, so with these letters only we are going to calculate the potential difference and then capacitance. Okay, so then the value of VAB, so the value of VAB, which is the potential difference between the conductors A and B, so this value will be equal to 1 by 2 pi epsilon naught into sigma m is equal to 1 to 6 you have to consider. Okay, so why? Because here there are a total of 6 conductors are there, right? So let it be 1, 2, 3, 4, 5, 6 like that. Okay, and here this value is qm into ln d bm by dam. Okay, so by using this expression you can calculate the value of VAB. Okay, so once you expand this here, right, here the conductors instead of representing 1 to 6, so here in the diagram they represented with A, B, C, A dash, B dash, C dash. Okay, A, B, C are the actual conductors, A dash, B dash, C dash are the image conductors. Okay, right. So now by using this expression, if you calculate the value of VAB, and the value of VAB you will get here will be 1 by 2 pi epsilon naught into QA ln D12 by R minus ln H12 by H1 plus QB ln R by D12 minus ln H2 by H12 plus QC ln D23 by D31 minus ln H23 by H31. Okay, so this formula you will get when you expand this equation, and also consider that the value of Q1, so these values are plus QA, this is plus QB, and this will be the plus QC, and this will be minus QA, this will be minus QB, this is minus QC. Okay, so by considering all of them you have to finally obtain this equation. Okay, and now from this equation you are getting this equation VAB is equal to 1 by 2 pi epsilon naught QA ln D equivalent by R minus ln H12 H23 H31 whole to the power of 1 by 3 by H1 H2 H3 whole to the power of 1 by 3, right? So if you solve this equation you are getting this equation plus QB into ln R by D equivalent minus ln H12 H2 H3 whole to the power of 1 by 3 by H12 H23 H31 whole to the power of 1 by 3. So this equation, and here the value of D equivalent is D12 D23 D31 whole to the power of 1 by 3, and this is also called as a equivalent equilateral spacing of the conductors. Okay, this D equivalent will be same when you are not considering the effect of earth. Okay, now this, after getting the value of VAB you can calculate the capacitance between the neutral. Okay, capacitance between any conductor to neutral, which is called the Cn here, and the value of Cn finally you are getting here is 2 pi epsilon naught by ln D equivalent by R minus ln H12 H23 H31 whole to the power of 1 by 3 by H1 H2 H3 whole to the power of 1 by 3. So which is the value in farads per meter, right? If you want to convert this farads per meter into microfarad per kilometer, so then you will get this equation which is the per phase capacitance, okay, or phase to neutral capacitance also you can say. So the value of Cn will be 0.0242 by log D equivalent by R minus log H12 H23 H31 whole to the power of 1 by 3 by H12 H2 H3 whole to the power of 1 by 3, right? So you can use any one of these two equations for calculating the capacitance of a three-phase transmission line by considering the effect of earth. Okay, right. So let us see one numerical problem so that we can understand the how to calculate the capacitance of a transmission line. Okay, by considering the effect of earth, right? So once if you read the problem, so here calculate the capacitance to neutral. Capacitance to neutral here is nothing but, so this is the per phase capacitance. Okay, so per phase capacitance you have to calculate it. So per phase capacitance you can determine with, you can denote with CAN or simply Cn also you can say. Okay, so on this value also you have to calculate per kilometer, so not per meter. Okay, so by with and without considering the effect of it, right? You have to calculate the per phase capacitance with considering the effect of it as well as without considering the effect of it. And the radius of the conductor is given here as 0.01 meters, and spacing between the conductors is given as 3.5 meters, and the conductors are 8 meters above the ground. Okay, so the data is given here. So if you take a single phase transmission line, okay, So now here you will be having the two conductors. Now these two conductors are spaced 3.5 meters apart, and if this is the earth, then the distance from ground will be 8 meters. Okay. So now if you are not considering the effect of earth, so then the value of capacitance, per phase capacitance, that value will be equal to 0.0242 by log d by r, so which is in microfarad per kilometers. Okay, and the value of d here is the spacing between the conductor, which is 3.5 meters, and r here is the radius of the conductor, so which is r is equal to 0.01 meters. Okay, so spacing between the conductors is 3.5 meters and radius of conductor is 0.01 meters. Here the units are the same, so we won't get any problem. Okay, so now these two values directly we are going to substitute in this equation. So then that equation can be written as C1n is equal to 0.0242 by log d here is 3.5 and r is 0.01. Right, so the value is in microfarads and this value is for 1 kilometer. Okay, so if you solve this total value with the calculator, so then you will get 0.00951 microfarads per kilometer. Right, so this is the value of per phase capacitance of the transmission line if you are not considering the effect of ground or effect of earth. Okay, now if you consider the effect of earth, how will be the value of capacitance? Okay, so when you consider the effect of earth here, we have to use the method of images. Okay, so according to the method of images, here for every conductor there will be another same conductor will be there as a image conductor which is below the ground, so at a distance same as the actual conductors. Right, so here 8 meters will be the h value, h is equal to 8 meters. Right, so now the capacitance by considering the effect of earth for a single phase transmission line, if you see, so this value is C12 is equal to 0.0121 by log capital D by small r into 1 plus d square by 4h square whole to the power of 1 by 2, and this value is in microfarads and the value is for 1 kilometer. Okay, so now this C12, so this C12 is line capacitance. So line to line capacitance, which you can also call it as line capacitance. Okay, right. So here the value of R is given, which is 0.01 meters, and the value of D, so which is the spacing between the conductors, is given, which is 3.5 meters, and the value of H will be, H here is the height from the earth. Okay, so the conductor height from the earth, which is given as 8 meters. Okay, all the values are given. Now we are going to substitute all these values in this expression. Okay, so this expression can be written as C1. So by considering the effect of earth, so C1 to earth will be equal to 0.0121 by log 3.5 by 0.01 into 1 plus 3.5 whole square by 4 into 8 square whole to the power of 1 by 2. So which is in microfarad per kilometer. Right, and this value if you calculate, so then what you will get, the value of C12 will be 0.00477 microfarads per kilometer you are getting. Okay, so this is the value of capacitance when you consider the effect of earth, and this value is not per phase capacitance, it is the line to line capacitance. So you have to convert this line to line capacitance into per phase capacitance. Right, the value of per phase capacitance, so which is C1n or C2n, this value will be equal to 2 times the value of capacitance between the lines, so which is 2 times the C12. Okay, so now C12 here is, it is 0.00477. So the value of C1n, so when you consider the earth, will be equal to 2 into this value, so which is 0.00477. Okay, so now if you calculate this value, so you will get 0.00954 you will get. Okay, so this is the value of capacitance when you consider the effect of earth, right? So if you are not considering the effect of earth, the value of capacitance here is 0.00951. Okay, so 0.00951. So this is the C1n value. So when we are not considering the effect of earth, so if you consider the effect of earth, this is the value. Now if you observe that these two capacitances, right? So the capacitance, the value of capacitance when you consider the effect of earth will be a slightly high value, right? So by this you can say that the value of capacitance, if you consider the effect of earth, will be increased to a small amount. Okay, so now if you find the ratio of these two, you will get how much will be that increment. Okay, so if you find the ratio of C1n, so which is the per phase capacitance by considering the effect of earth by C1n without considering the effect of earth, and C1n by considering the effect of earth, you are getting 0.00954 you are getting, and without considering the effect of earth, the value 0.00951. Okay, now if you calculate this value, you are getting this value will be, this ratio will be equal to 1.0042. So the value of C1n earth, this value will be equal to 1.0042 times the value of C1n. Okay, so the value of per phase capacitance when you consider the effect of earth will be 1.0042 times the value of C1n for this case. Okay, so from this you can say that, so this C1n when you consider the effect of earth, so will be higher in what much amount? 0.0042 times the C1n. Okay, so which is nothing but 0.42%, right? So the presence of earth will increase the capacitance of the transmission line by 0.42%. So this 0.42% is a very small amount, right? So because of that reason, so this value can be neglected in the calculations, right? So which means that the effect of earth will be generally neglected for while calculating the effect of while calculating the capacitance. Okay, so why? Because when you consider the effect of earth, the value of capacitance will be increased, but that increased amount is very less amount. So because of that reason only, so for small transmission lines, you can generally neglect the effect of earth. Okay, right. So thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.